Okay, hello everyone. Welcome back to the meeting, ICRANet-ISFAHAN Astronomy meeting. We are starting soon the third session of the meeting. And in this session, we are inviting Professor Liu from Nanjing University to talk about the origin of high-energy galactic cosmic rays. He has 30 minutes to go, and I believe the session is going to be recorded. I don't see the recording sign. The morning session was being recorded. Maybe they want to record it again. But anyway, the floor is yours, please. Thank you.
Okay, thank you very much for the introduction. And I would also like to thank the organizer for the invitation. Thank Soros. So today I'm going to talk about the high-energy galactic cosmic rays, but from the perspective of recent ultra-energy gamma ray observations. Okay, so in general, we will call a photon with energy above 0.1 MeV as gamma rays. But this boundary is not so strict, so someone also calls this energy as soft, hard X-ray or soft gamma ray. But anyway, in general, energy above this 0.1 MeV is considered belong to gamma ray. And when energy goes to 0.1 GeV, we enter the high energy gamma ray regime, and it goes to 3 orders higher to 0.1 TeV. We call it a very high energy. And ultra high energy gamma ray, it means it's defined as the gamma ray with energy above 0.1 PeV or 100 TeV. So actually, this is a new research direction because the first ultra energy gamma ray sources is detected only 2 years ago. I mean, for ultra energy gamma source means the significance of the detection is about 5 sigma. Before there were some other signal, but not reach so high significance. So here comes my outline. So I'm going to talk about the relation between cosmic rays and ultra energy gamma ray emissions. Then I will give some example of the detected ultra energy gamma ray sources, including the famous Crab Nebula and the 3 brightest ultra energy gamma ray sources at 100 TeV energy. Then I will talk about the recent discovery of this diffuse galactic gamma ray emission above 100 TeV. Lastly, I will give the summary. So, okay, so what is the cosmic rays? So generally speaking, they are energetic charged particles from the outer space. And by number, they are mostly composed of protons. And in the right this right panel shows the spectrum of a locally measured cosmic ray. We can see the spectrum extend from 1 GeV to up to near beyond 10 to 11 GeV or 10 to 20 EV. So in this cosmic spectrum, we see 2 distinct features. One is the break here, and another is a hardening, flattening feature here. So the break here is also called a knee because it looks like the human's leg, and here is the knee. So below the knee is appear at energy around 1 PeV or 10 to 15 EV here. So particles, cosmic ray below the knee is considered to originate from galactic sources. Why cosmic rays with energy beyond the ankle? So here, which is considered to be extragalactic origin. And the cosmic ray in between are thought to be a mixture of these 2 origins. So it's important to find the origin of the cosmic ray at the D energy. The detection of these energetic particles means that the existence of the very energetic particle accelerator in our universe. We can see here this is about 10 TeV. This is the energy limit that could be reached by the largest particle accelerator in Earth. This is the LHC, can accelerate proton to 10 TeV. So cosmic rays, so it means in our universe, there are powerful accelerators that can easily exceed the maximum energy of LHC. So to find out these sources and study their properties is very important to understand those extreme processes in the universe and understand their underlying physics. On the other hand, in our galaxy, cosmic rays is a very important component, because by terms of the energy density, it constitutes about 1/3 of the energy density in the interstellar medium. So it has important feedback on the galaxy and the star formation, and also dominates the chemistry of the interstellar medium. So understand the origin of cosmic rays is also important to understand the galaxy's evolution and even the evolution of our universe. The cosmic ray actually is initially detected at more than 100 years ago, but so far we have not had a clear understanding on its sources. This is because the deflection by the magnetic field in the space, because cosmic rays are charged particles, when they propagate from the source to Earth, they will be deflected. Their trajectory will be deflected by magnetic field. So when a cosmic ray arrives at the Earth, its arrival direction does not point back to its true source location. So in this source, this added the difficulty to finding the cosmic ray sources. Then people came up with an idea to search for the photons or neutrinos emitted by these cosmic rays, because these particles, they are charged particles. They are neutral particles, so they will not be infected by the magnetic field. And if we identify these signals from some sources, then we can pinpoint the cosmic ray sources. So for ultra-energy gamma ray emission, there are basically two mechanisms in our galaxy. In the galactic source to produce ultra-energy gamma ray emission. So one is a hydronic process, and another is an Epoch process. For the hydronic process, it's called the proton-proton collision. It's a high-energy cosmic ray interact with some, such as the molecular gas, interact with interact with the atomic. Then it can produce pions. The pions usually take about 20% of the parent proton's energy. Then if the pion is neutral pion, it will decay into a gamma ray photon, and each photon takes about 10% of the parent proton's energy. So the figure here shows the gamma ray spectrum produced in a single proton-proton collision. We can see the spectrum peaks at 0.1 here, where this is in unit of the parent proton's energy. So it means typical energy of the produced photon in this way is about 10% of proton's energy. And for the Leptonic process, it's so-called inverse competence scattering. So this electron will scatter with a low energy photon and pass their energy to the low energy photon, make it to very high energy. So here shows the relation between the mean upscatter photon energy and the electron energy. We can see if we want to produce gamma ray with energy above 100 TeV here, then basically we need the electron energy is beyond 300 TeV. So in this sense, we can see the ultra energy gamma ray is the probe of a PeV particle accelerator. So if we want to understand the origin of the PeV cosmic rays, then our aim is to search gamma ray sources above like 100 TeV. So here shows the recent publication by the LASSO experiment. So LASSO is a ultra energy gamma ray detector. Actually, it can also detect the TeV can detect gamma ray from TeV to PeV energy. So this is a detector in this Tibet Plateau in China. And this is, so here we can see there's some excess of this gamma ray emission in the galactic plane, which is in this way, in this position. If we look at into this region, we can see so this color map shows the LASSO's detection. While this cyan circle shows the previously detected source as the TeV energy. So we can see some of the LASSO this ultra energy gamma ray source is well consistent with this previously TeV source in spatial. But also there are some of them without any, for example, this one, without any previous detected TeV sources. And so here shows the two tables summarize the detection. So in the upper panel, it shows the source list and with the position and the significance and the maximum photon energy from the source, and also the gamma ray flux at 100 TeV. So the first one, the first row is this source is the Crab Nebula, and actually this is the only two sources with photon detection with energy above 1 PeV. Another source with detection with photon above 1 PeV is this one. This is the Cygnus cocoon, which is also a famous source. In the table down here, we try to find some associating astrophysical counterparts for this ultra-energy gamma ray sources. Except the first one, the Crab Nebula is firmly identified. Other sources are not, the astrophysical counterpart is not so clear because they are extended source and they are in spatial coincidence with more than one astroparticle, for astrophysical counterparts. But we can see for most of the sources associated with the ultra-energy gamma ray sources, there are this pulsars, which is this fast rotating neutron stars with a high magnetic field. And another type is this SNR, is the so-called Dry Remnant, which is born from the death of the massive star or due to the accretion of this white dwarf. So this kind of source, they were in the explosion, it will drive very strong blast wave, and it's a sweep through the circular medium and can accelerate these particles by the shock. And the other another candidate source is this star forming region, massive star forming region actually. So there are many hundreds of this very massive star forming here, and because of their high luminosity, due to this radiation pressure, they drive the material in the surface of the star away to form this very strong stellar wind. And this wind can also form shocks and accelerate particles. They sweat up. So then let's look into some sources. First is this Crab Nebula. So this figure shows the observation of Crab Nebula in different energy band. Actually, Crab Nebula is a well-studied, probably the most extensively studied source in astronomy. This is it is powered by a very energetic pulsar here, and born in a supernova explosion about 1,000 years ago. So China, we know China is has a long history with old civilization as Persia. So the astronomer as old Asian China, they record this supernova explosion in this chronicle book. For example, in the book here, they recorded the appearing time of the supernova explosion and the position in the sky, and also the duration of this the brightening of the star, and also it recorded this brightening of the star disappear only after more than 1 year. So from this, people can also, people today, astronomers today, can derive some information from the supernova explosion related to Crab Nebula. In half century ago, the Crab Nebula is a very popular topic. At that time, this British astronomer Geoffrey Burbidge said there are two kinds of astronomy: the astronomy of Crab Nebula and the astronomy of everything else. So we say this is a very hot topic at that time. And today, of course, the Crab Nebula is not so hot. The topic is not so hot as half century ago, but still it usually bring us many surprise. For example, this Crab Nebula actually is the first ultra-energy gamma ray sources detected. This is the paper published in 2019 by the Tibet S-gamma experiment. It's another gamma ray detector located in Tibet plateau. And in this paper, they derive they extract the spectrum in this Crab Nebula region, and we can see the spectrum extends to 300 TeV, and before the highest energy point is still below the 100 TeV. So here is a little bit physics. So this pulsar, the Crab Nebula is powered by this so-called Crab pulsar. It is the most energetic pulsar detected in our galaxy, with this spin-down luminosity about 5 × 10⁻38 erg/second. So during the pulsar spin-down, it converts the spin-down energy, it's a rotational energy, to the magnetic energy and the electron energy. So as the cartoon show here, when this fast rotating star, he dragged this strong magnetic field to rotate together with him. Then it drives this very energetic pointing flux, and this pointing flux also bring the electron-positron pairs in the magnetosphere away. And at some point, but by certain mechanism, but this is still an open question. But anyway, people find as during via certain mechanism, then the magnetic flux were converted to the kinetic flux of these electron-positron pairs, and form a very strong this ultra-relativistic electron-positron wind. And when this wind collide with the ambient medium, usually this ejector of the supernova explosion, and it forms a termination shock and accelerated these particles further into very energetic particles and form this long thermal emission, as indicated by this blue region here. And there are many of studies for the origin of this high energy emission from the Crab Nebula. So some people speculate that whether this proton could be also accelerated in this process and form some and give birth to some ultra energy radiation. So based on the previous study, people find the proton fraction that's contained in the Crab Nebula today is only about 0.5% of this total spin-down energy loosed by the Crab pulsar. And NASA's measurement on Crab Nebula gives us some new clues. So from this spectrum, we can see the NASA's measurement extend the spectrum up to 1.1 PeV, and generally it is consistent with this leptonic model, where the high energy gamma ray radiation are explained as the inverse confidence scattering. But if we look closely to this this highest energy part, we see actually some deviation from this model prediction. So then people think there may be another component contributing to this high energy part, because we see here is some kind of hardening of the spectrum. So this second, if there exists a second spectrum component, it could be either a leptonic component or a hydronic component. So currently we cannot distinguish of them. Then we may ask, so previously people obtained the protons that are currently confined in the Crab Nebula. It's 0.5%. The energy is 0.5% of the total spin-down luminosity. But proton injected at an early time may have already escaped the Crab Nebula. So the entire energy that goes from the spin-down energy to proton energy could be even higher. So in this case, then we need to study the escape of the particle from the Crab Nebula. So based on the constraint on the so-called diffusion coefficient, then we model the fraction of protons that are still confined in the Crab Nebula today, and then we use this two-component spectrum to fit this mirrored spectrum, with one leptonic component fitting the energy, the spectrum below 300 TeV, and a hydronic component explain the energy beyond 300 TeV to explain this possible hardening. And by normalizing the hydronic flux at 1 PeV, mirrored flux at 1 PeV here, we can obtain the fraction of this proton's energy can be as high as 10 to 50% of the total spin-down luminosity, the spin-down energy. this given on this different parameters. So this will gives us an interesting implication. Is this a contribution of cosmic ray beyond the need? Because in this case, if we want to explain the PV gamma ray emission by the protons contribution, it means the proton's energy accelerated in the Crab Nebula must exceed 10 PeV. The energy exceeds 10 PeV. And if this proton have largely escaped the Crab Nebula, they will become cosmic rays. So we did some calculation based on the propagation time and the interstellar this diffusion coefficient in the interstellar medium. We find that the proton escape from the Crab Nebula have not already arrived at the Earth today. But if all the pulsars, older pulsars in the galaxy, they have same fraction, energy fraction converted into protons, then the collection of all the pulsars, they could contribute a large fraction of the measured cosmic ray proton component beyond 1 PeV, as measured by this is measured by the cascade ground experiment, and the pulsars contribution in principle can explain this measurement. Okay, I'll skip this. Okay, then let's go to these three brightest sources at 100 TeV. So actually, these three sources, we have this the name of LASSO here. They are even brighter than Crab Nebula at 100 TeV. So, but they are extended sources. So there are more than one astrophysical counterparts in spatial coincidence with these sources. So currently, we still don't know which sources contribute the ultra energy gamma rays here. But from these three, from the spectrum measured by LASSO, we can see all these three sources shows a gradual softening of this spectrum, but without a clear spectral cutoff at high energy. So in principle, this spectrum can continue to even higher energy. So first source I want to talk about is this G2226. So this in this region, it contains a superlunar remnant and also a very energetic pulsar with this luminosity of about 5% of the Crab pulsar's luminosity. So here, this figure summarizes the current observation. This green contour shows the radio observation. People think this is the shows the superlunar remnant, and in the northwest part, we can see the pulsar is located here, and this have this dense radio contour in radio is this Boomerang Nebula, which is powered by this pulsar, and these circles means the observation of the very high energy and ultra energy experiment. This gamma ray source location is consistent at this southwest part, which is called the tail, and this part is called head. And this blue color means the atomic distribution of the atomic cloud around this superlunar remnant, while this red color means the molecular cloud distribution. In the head region of this structure, we see the interaction between this superlunar remnant with the atomic cloud. So this is probably the reason why this superlunar remnant shows this highly asymmetric morphology. And it is worth to mention that all the gamma ray emission, actually the centroid of the gamma ray emission is consistent with this molecular cloud in the tail region. So this actually is favors the hydronic origin of the ultra energy gamma ray detected here. And the X-ray observation also shows very interesting results. So here, this figure shows the intensity profile means the intensity of the X-ray emission as a function of the distance to the pulsar. Here we see the intensity profile drops quickly at the beginning at this head region, but it becomes flat at this tail region here. So this flattening also shows in the gamma ray index here. In the X-ray index here. This means the separate origin of the X-ray emission here and here. And the most plausible source for the X-ray emission here is the superlunar remnant shock. And based on the spectrum, we can infer that the shock velocity is at least 3,000 kilometers per second. And with this fast shock, it is sufficient to accelerate the protons up to 3 PeV. So makes this source a very promising PeV proton accelerator. So here shows the spectral SED modeling. We can see the hydronic component here can interpret well the observed gamma ray emission. So this is a general feature of this source. So the pulsar is here, and the supernovae explosion probably also occur here. But at this part, the expansion of the supernovae remnant is stopped by the at least decelerated very fast by this dense atomic cloud. And in this side, there is an atomic cloud cavity. So this supernovae remnant can expand very fast to this way and drive strong shocks. And when accelerated protons escape from the shock, they can escape to this position of the molecular cloud and produce a gamma ray here. So if we look this system in this way, then we'll see the observed this a very asymmetric feature of this supernovae remnant. Okay, the second source I want to talk about is this J1908. So this region also contains one supernovae remnant and two energetic pulsars. This is the radio observation shows the share of the supernovae remnant, and we have one pulsar inside, and another pulsar is about 0.5 degree away from here. And the Veritas observation on the very high energy gamma ray emission shows that the gamma ray emission here it can be divided into two parts. One is surrounded the supernovae remnant, and the other is surrounded the pulsar below. And this is a Hawks observation. Also, they have a strong detection in this region. At a lower energy, at this GeV observation by Fermi-Let, we also see interesting feature. So at 0.1 GeV, at low energy gamma ray, we can see the centroid of the emission is close to the supernovae remnant. While the emission beyond the 30 GeV, it also looks like being divided into two parts, which is similar to the Veritas emission. So from the spectrum, we can also see the two components, one bump here and another hardening. So if we combine the GeV emission with the TeV emission, we see these two humps here. And the low energy emission, since it is associated with the supernovae remnant here, and also we can see there are very dense gas around the supernovae remnant. So this is probably due to the hydronic by proton-proton emission or the Bremsstrahlung emission, which are related to the gas density. And at the high energy, the hump here is probably the pulsar nebula by electrons. One thing I want to mention here is that IceCube have they put an upper limit on the neutrino flux in this source. The upper limit is shown here because protons are gamma rays are produced coincident with the neutrinos. So we can also expect, so it also allows a gamma ray component at this level, which could not be detected today. So actually in this ICRC this year, by a Hawks experiment, they find a possible indication of the hardening of the spectrum above 100 TeV. So this may indicate a possible hydronic component here. The last source is this J1825. This region contains two energetic pulsars. One is separated at 0.5 degree. So this source, the right panel shows the Hess observation beyond above 1 TeV in this source. We can see some interesting feature. One is this isotropic morphology. The pulsar is here and it's largely extended towards the southwest part. And also we see this energy dependent morphology. When energy goes higher and higher, this source shrinks and it shrinks to the pulsar's location. This is consistent with the leptonic origin because this high energy, they cool faster. They cannot propagate to larger distance. And another very interesting feature is this spatial extension of this source. We can see the spatial extension is beyond 100 parseconds. And this is very difficult to explain. I mean, it requires a very rapidly rotating pulsar with a period rotation period smaller than 1 millisecond at the beginning. Only in this extreme condition we can get a pulsar nebula at such a large extension. So another possibility is that some electrons accelerated in the Ptolemaic nebula, they escape the Ptolemaic nebula and propagate to the much larger space and produce this extended region. And the Ptolemaic nebula itself is still not that extended. So under this scenario, we can fit like the spectrum and the surface brightness profile, and also the energy-dependent morphology of these sources. So okay, so I think I don't have time to talk about
Professor Liu, I think it's been 30 minutes. I just wanted to.
Yes. I just okay. So just one more page here. So this is a measurement, recent measurement by Hawk's experiment. They find in this region there could be a third there could be three components gamma emission here, with one between the two pulsars, which I talked about. So the spectrum with this component is very hard, and also there are a molecular cloud in this region. So this makes it implies there could also be PeV proton accelerator in this region. Okay, so I will jump to the summary. So sorry for the delays.
That's all right.
Thank you very much. Sorry.
Well, thank you very much. Thanks for the presentation. Obviously, you had a lot of results you wanted to share. We appreciate that. So we don't have much time, but if there is any question, I think we can at least have one question.
Well, just to say that these laser data are just splendid and very, very important. And they show very clearly that the case of the crab with the two components is far from an exception, but is a rule. We are working very much in this direction, and we would like to continue with special dedicated workshop on this topic, and we are very grateful to the people of Nankin and the LASO group to have presented this splendid data in this occasion.
Thank you. Actually, I think this is an important feature that probably we may be to identify in maybe 2 or 3 years. And also we will also continue to search for such kind of feature in other young and energetic pulsars. So probably this could be a common feature.
And we are looking to a theoretical interpretation of this structure. Therefore, we have to keep in touch closely.
Okay.
Wang Liu is just arriving from China, landed in Rome. He will be in few hours in Pescara, and we are working precisely on this topic. But we will record all this marvelous lecture all together and publish as soon as possible. Thanks.
Thank you.
Excellent. Excellent.
Thank you.
Thank you very much. Thanks for the comments as well. I'd like to thank Professor Liu again and give the floor to Dr. Narek Sahakyan, who's going to be talking about multi-wavelength observations of blazars. If he has access to present his slides, it would be appreciated.
Yes, I cannot share the screen, actually.
Just a moment, Narek. I will give you just a moment.
Yes. Okay, good.
Okay, where are you now, Narek? Are you in
Armenia? Yes. Remember, we met several years ago.
I'm sure. Yeah, exactly. It was the first joint workshop with Armenia.
Exactly. Yes, we
Excellent.
had.
Nice to see you, and
Yes.
take the floor.
Thank you very much, Soros, but I'm not still able to share my screen.
No, you have permission. You have permission now.
Yeah, just click on that share button.
It's not active. The button is not active.
I think you activated me, Soros. I think you should activate Narek.
I see that the screen is, this button is not active. So, Soros, can you activate me?
Yes,
you are a presenter.
I gave you the high-level permission. You are organizer now, Narek. The highest level of permission you have.
Okay, thank you. Thank you. Okay. So
you are on top of everybody. Now go ahead. Thank you.
So you see my slides, yes?
Yes.
Now.
Yes. Yes, we have it.
Okay.
Yes.
Thank you very much. I'm very happy to present in this ICRANet-ISFAHAN meeting. I remember several years ago when we visited ISFAHAN with Professor Ruffini, we enjoyed very much. So I hope in the future, when the pandemic situation will be better, so we will be present in ISFAHAN, that we can enjoy also this beautiful city. So I'm going to start, I'm going to speak about multi-wavelength and multi-messenger view of blazars. Just very short note, what are blazars? So this talk I will speak about extragalactic sources. The previous talk was about the cosmic rays from galactic sources, but now I will speak about the extragalactic sources. So as we all know, AGNs are the luminous galaxies that they have the central nuclear part is very bright. It's so bright that it exceeds the emission from the other parts of the galaxy. This nuclear central part is believed to be powered from the supermassive black hole, as this morning Professor Ruffini mentioned. And in some AGNs from these central nuclear parts, we see that these linear structures that are extending, these are jets, and they are a very intense injection of the particles. According to the current classification of the AGNs, different type of the sources like Cepheid galaxies, radio galaxies, or etc. These are the same object, but we are just looking to them from different directions, and this is why they appear differently. In this presentation, I will mostly speak about blazars. So these are the special and most extreme type of the AGNs, and this is when you have this the jet that is making very small, or is just the direction of the observer. So because of this small inclination angle, this radiation from the jet is relativistically Doppler boosted, and it dominates from the emission from the other components of the galaxy. And because of this jet small direction, we see many different properties of these sources, such like extreme variability in almost all frequencies. So there are different ways, different methods to classify, to divide these blazars, but the two main classes, these are flat spectrum radio quasars and BLAC objects. So this is based on the optical spectra of these sources. So in the case of FSRQs, you see that emission lines, and this means that there are some internal structure inside the nuclei, while for the BLACs, they are featureless in optical band, so you don't see any emission lines. And this division of two types also affects the origin from these sources, which I'll show in a few slides. This is a diagram that shows the main difference when you have the jetted AGNs, I mean AGNs which show this jet structure, and ones that they don't have. So you see that when the AGN does not have a jet, this is this black lines here. Their emission could reach up to X-ray band, let's say in the best cases, while when you have these jetted AGNs, the emission goes all the way from radio to high or very high energy gamma ray band. So this means that we have this very large, like 10 to 20, 21 hertz window that we could observe these sources, put all that together, and have a picture of the processes that is happening in these sources. As I mentioned, one of the distinguished features of the blazars is the variability, that is the flux changes in different bands. So in this diagram here is shown one of the famous blazars, this 3C454.3, and its emission in gamma ray, top two panels, X-ray and optical and UV bands. You see that variability, the first panel here, you see that in the gamma ray band, this variation, the flux variation is almost 2 orders of magnitude. So sometimes the source gets really, very bright. So it's more than 10 to minus 5 photon per centimeter square per second minus 1, which is among the top brightest sources detected in the gamma ray band by Fermi telescope. The same also is true for the X-ray band. When you see so sometimes the flux reaches really very high level, and the same also in the optical and UV band. Of course, this is not necessarily that this brightening in different bands are related to each other. So there could be some delay, and from the correlation, possible correlation or anti-correlation, it also depends the origin of the emission. Recently with Paolo Giomi, we have introduced a new type of blazars that we call transient blasters. So what is the unique feature of this type of the sources that I'm going to show you in this animation? As you in the top of this plot, I show the light curve. So it is gamma ray flux observed in different times, and in the plot below is the spectrum of this source. So this is a very small interval of the time, around 2017-18. So you see that initially the source is almost invisible in all the bands. Suddenly it gets bright, it emits in the gamma ray, optical, UV, in radio also. It is very strong in the gamma ray band, very bright in the X-ray band. For some 6 months, 7 months, it emits very brightly, then its flux gets down and the source completely disappears. So it is not anymore observable, not in the X-ray band, not in the gamma ray band. So this is more clear from this plot on the left, that you see that we show the flux at 1 GeV and at 1 keV. So also in the early observations in 1990s by RAS instruments, you see that there was no any sign of the X-ray emission from this source. So this always was believed to be an AGN or blazar that is not emitting in the X-ray or gamma ray. But suddenly in 2018, 2017, 18, it starts to be very bright in gamma ray. X-ray band is observed by several instruments and disappears. As a comparison on the right side, you see that the spectrum of this source with green is just compared with the highest and lowest X-ray fluxes of very well-known blazar, Markarian 500-01. You see that there is a 2 order of magnitude difference. So when this source was bright, it was among the brightest X-ray source in the sky. So if this type of blazars, these transient blazars, are indeed present, there are few examples like this. We are working with Paolo to identify new candidates. So this means that whatever we were computing based on some population of blazars, they need to be redone because there are much more sources that are not active now. We don't see them, but in one day they could be just bright and emit in X-ray or gamma ray band. So this is general introduction about blazars. So what now from the theoretical part? This is the spectrum of Markarian 421, which was discovered by Markarian here in Burakan. But then it will appear to be one of the most bright and well-studied blazars in the sky. So you see that this is the spectrum measured from radio to high-energy gamma ray and very high-energy gamma ray band, and data taken from different instruments, from ground, satellite, etc. And so now the general theory is that this first peak, and you see that there are 2 well peaks in this spectrum, one in around X-ray or optical band, and the next one in the high-energy band. So according to the current theories, the first peak is explained by synchrotron emission of the electrons that are accelerated inside this jet of this source. While for the second one, basically there are 2 different scenarios. One is leptonic, when again the emission comes from the electrons that are accelerated into the jet, and from Hydronic interactions. Based on the particle that is producing this emission, there are 2 different theories, let's say leptonic or hadronic. So now the most interesting question is to distinguish when we have leptonic or when we have the hadronic emission. So in the case of leptonic scenarios, are more simple. So when you have BLX that have no emission lines, the picture is very simple. So you have the emission zone that is moving inside the jet. You have the electrons that are emitting by synchrotron emission, and these photons interact again with the same electrons and inverse Compton scatter them to the very high energies by this synchrotron quantum process, and you form the second peak in the spectrum of the source. So this is the case when it's very simple, but when you move to FSRQs that have this internal structure, so this inverse Compton, again, the first component is the synchrotron emission, but the second one is depending where is the emission region from the central source. So depending on this location of this emission region, different component could contribute and can dominate to the emission. For example, this is shown an ACD of this famous blazar 3C454. You see that it's composed by the inverse Compton scattering of the synchrotron photons, which is the green dashed line. It can also from the photons reflected from broadline region, which is the orange one, and from the photons that are directly emitted from the disk. So when you have the emission region that is moving from the central black hole, these components are dominating. One is going down and another one is going up. So it's changing depending on the location of the emission region. From the leptonic point of view, now we have so much data accumulated from the observation of these sources because they are always present, and we can really make very detailed and deep study of the emission processes. So one of such study I present here. So what is done here is the data between 2008 and between 2018, so 10 years of data, is divided by the intervals when you have a simultaneous data in optical, X-ray, and gamma ray band. So in the end, you form like 520 different spectral energy distributions, and you can model them and to see how during the time this emission is evolving. So this means that the data allows not only to model the specific ACDs at a given moment, but also to see how the dynamical is changing the radiation in different periods. As you can see in this animation, sometimes the different components are going down, going up, and this is the connected to the variability of the source that we see in different bands. So the domination or contribution from one component, it means that you see the brightening in the X-ray band or in the optical or in the gamma ray band. So this allows us to get to see how the emission in the source is changing during the time, which is very crucial because what we can do actually from the modeling of all of these spectra, we can estimate many different parameters, and these parameters are very crucial for understanding the processes in these relativistic jets. For example, from this modeling, you can estimate the power law indexes of the emitting electrons, which are characterizing the processes that were responsible for acceleration or cooling of particles, and you see how they are changing in time. You can estimate the Doppler boosting factor, which allows you to understand the speed, the velocity of the component inside the jet, even the magnetic field, which is directly connected to the state of the plasma in the jet, also the jet luminosities, etc. So this is a complete picture that allows you to have a deep study of this object. So this is one example that I just showed, but there are so many data from so many blazars that we are currently studying, and we are making such modeling for different objects and accumulating a lot of information also from the dynamical point of view to see how this emission process is changing in time. So this is about the leptonic processes. So more or less everything is a little bit clear because we have the data. This data could be modeled using different models. You can estimate many different parameters, and based on these parameters, you can make a different conclusion. So from the blazar research, there was a change, a new era when there was this blazar, the KS-0506 observed. So what is the point and what is the change? So many of you know that in 2017, September 22, there was a neutrino detected by IceCube detector, which is in South Pole. The energy of this event was 290 TeV. But the most important in this case is not the energy of this event, because much more energetic events were observed, but is the direction that is overlapping with is in the same direction of a blazar that was in a flaring state, which showed magic observation. Then there were many different instruments that they were observing the same blazar, collected this beautiful picture that is shown on here on the right side. And from the multi-messenger point of view, this is the most detailed picture of a blazar, because you have the data both from the electromagnetic window and also from the neutrino constraints. So this allows you very deep investigation of processes in this jet of this particular blazar. But what was more interesting, when this IceCube collaboration, they looked back to the data, they saw that in 2014-15, from the same direction, from the same source, there was 13 plus minus 5 events above the background, which at that moment they were not reported because the detection significance was 3.5 sigma. But now when you know that there is a source that is emitting neutrino, these results are more than convincing. So this makes the first example when there were neutrinos detected, not only one, but few events from the same source. So now if we know that there are neutrinos and we should understand the processes responsible for this neutrino emission. So it could be either from proton-proton interaction or photon-hadron interaction. So in this first case, you don't need to have protons that are accelerated to the very high energies. Let's say 10 PeV or 100 PeV protons should be enough to produce this. But instead, in the other cases, when you consider photohadronic interactions, you need to have these ultra-high energy cosmic rays. So we know that these energies of these ultra-high energy cosmic rays are up to above 10 to 20 eV. So, and the jets of AGNs are considered the possible seats where these ultra-high energy cosmic rays can be accelerated. So once you have the protons that are thus accelerated to 10 to 20 electron volt, what is happening? They are losing the energy either via proton synchrotron emission or by photopion production. So in all cases, you produce the secondary particles, and these secondary pions, they decay, producing neutrinos, and there is another channel that is producing electromagnetic component. So as a comparison with the leptonic cases, in this hadronic interpretation is a little bit more complex, because we can show in this animation. So imagine that you have protons and electrons that they are accelerated in the jet. Under the magnetic field, these electrons are emitting the synchrotron photons. Then these photons interact with the accelerated protons, which are at ultra high energies. They produce the secondary pions, and the pi zero immediately decays to 2 photons. Instead, neutrinos or muons are produced from the charged pions. The same situation is happening when you have that the photons are just entering inside the jet from the external sources. And again, they are interacting, producing these pions. But we need to remember that cross-section of gamma-gamma interaction is much, much larger than the cross-section of pi-gamma interaction. So these photons that are produced, they are not easily escaping from the region. So what they do is they interact with again with the photons, they produce the electron-positron pairs, which themselves they interact, produce the photons, and so on. So you have the cascade that is developing, and this process is continuing until the point that the energy of the photons is not enough to produce the secondary electron-positron pairs. So instead of the leptonic case, when you have the simple interaction between leptons, photons, or magnetic field, in this case it's more complicated. You have many different types of particles, and you have to all consider them. So this is why with some collaborators, we developed this numerical code, which is called Soprano, that allows to follow time-dependent modeling of these leptohadronic processes in relativistic objects. So this code is in Python or C-based, and is fully time-dependent, which is very important and very difficult. Now I'll show in a few slides. Has a Python interface that is very easy to use, has all the most heavy interactions are done in C, because this will allow us to speed up the computation, and has a modular structure. So which is good that you could add, remove any process that you are interested, and you can see how your spectrum is changing because of one process is missing or is added. And what is more important, that it follows in each step energy conservation, particle number conservation, whenever is needed, because otherwise you risk to lose some part of the energy, and that will be problem for the later in modeling. Since we are dealing with many different particles and which are interacting in different time scales. For example, when you have the decay of the pi zero, it is in 10 to 16 seconds, minus 10 to minus 16 seconds, sorry. Instead, the synchrotron emission of the electrons in 1 Gauss magnetic field is like 1 day or 10 days. So you need to have the proper temporal discretization to follow all these things. So you have to have energy discretization to be able to compute in each step for all the processes. So we use different grids for different type of particles, for hadrons, neutrinos, leptons, or photons, and all of them are divided in 100 or more than intervals. And if you collect all of them together, you have something like 10 to 8 triple to quadruple integrals that you have to properly follow and compute them. This is what the most difficulty of this hadronic codes, because you have a lot of heavy integration that you have to follow. So if easily I show in this interaction chart which processes are involved and how we take into account them. So initially you have photons that they are produced from the synchrotron emission or from all charged particles. These are muons, protons, electrons, etc. These photons themselves, they interact with the protons or they interact with the neutrons, and from these they are producing neutral pions or charged pions. Then these neutral pions, they also produce photons. Instead, charged pions, they produce muons, neutrinos, and electrons, and so on. Then, so the photons can interact with the protons and produce again electrons. And these electrons are producing again photons. So you have this loop of different interaction of particles that you need to properly take into account in order to be able to compute how the cascade is developing in time. So in order to follow all the processes, for each process we wrote these kinetic equations, which include the injection of the particles, the possible cooling, and possible escape from the region. And these kinetic equations are connected one to other one and non-linear and non-trivial ways, and they should be solved consistently in the sense that one term that is losing term for the particles, cooling for one type of particles, it is exactly injection term for the other ones. So you need to really follow all of these cooling and injection of particles to not miss any part of the interaction. So all of these are done in our code, and it allows to, for any case of the particle injection, to compute the spectrum that you will see after the propagation of this cascade. And since this is time dependent, you can compute it in any given moment, at any given step, and then you can you see how in time is forming the spectrum of this source. There is a page of this code, which is here below in red that you can see, and so there is the article that is accepted in MRAS, and where all the processes, cross sections, kinetic equation, etc., are all described. So if you have any questions.
Thank you very much, Narek. A very timely presentation. So I would like to ask our audience to ask any questions if they have.
Very energy gamma ray band. Then you compute the possible contribution from the other parts of the other components, and you are able to compute the number of the neutrinos. And for some parameters that are listed here, you can just estimate the number of the expected neutrinos, and you can explain this one event. You can also model this within this so-called hybrid lepto-hadronic model. So when you have the electrons are contributing in this Fermi and magic band, while the proton contribution by cascade is moved to the lower energy band, in the X-ray band, and they are constrained by X-ray data. And these X-rays are putting a strong constraint on your data, and you can estimate the number of neutrinos expected as well. In this case, also by some parameters, you can get one event as observed by IceCube. The most difficulties, the most problematic cases are when you have these neutrino events. So a few 13 events. So you try different scenarios. You different set of parameters. You can get even very extreme values, like the proton luminosity above around 10 to 52 erg per second. But in any way, you are not able to explain more than 3-4 events with this limit that is imposed by the X-ray observations. So this X-ray is putting a really strong constraint on you are not able to reach the level of 10 neutrinos, let's say, from this source with the current data. Actually, this is not only our model that is predicting these things. There are many different models that were applied in, and all of them actually reaching the same conclusion, in the sense that when you have one event, you can count this neutrino emission. But when there are more than few events, there are difficulties to model this. Of course, there are some alternative theories as well. In principle, for example, when you have these jet target interactions, so this is when you have the dense matter that is entrapped inside the jet. In that case, the protons they don't need to be accelerated to ultra-high energies. They can interact, producing again gamma rays and neutrinos. There are different scenarios. What could be this dense matter? But
so it seems he has some problem with his connection.
Yes, I seem to. Narek, do you hear me well?
Conclusion is the same, that even if you have, if you try to compute the number of the neutrinos, even in these scenarios, you are able to
Narek?
Sorry?
Narek, do you hear me?
Can you hear me?
Yes, we had a
Yes, can you hear me? Sorry.
break. Yeah, we had
Yes,
we lost you for your voice for twice actually in the last few minutes. I just wanted to say you that the time is approaching to the end for your talk. If you want to wrap it up, that would be great. Thank you.
Yes. I'll just. Can you hear me now? Yes.
Yes, absolutely. Yes. Go on.
Okay, I'll finish in 1 or 2 minutes. So what is interesting in this source that when these neutrinos were observed, it was the X-ray peak. The first peak was above X-ray band, so implying the source was in extreme blazars, which is very interesting because extreme blazars are always considered to be the sources where ultra-high energy cosmic rays can be accelerated. So whenever you try to model this with different assumptions, using different parameters, you can get neutrinos, but this extreme X-ray state was too short and you cannot reach this level of neutrinos that were observed by IceCube instrument. So I'll just come to the, very short here. This observation of the blazar using 2 different windows from neutrinos and from the photons actually was good because it was able to see this jet using 2 different windows, but at the same time it was introduced with additional difficulties because it seems that when we have more than 1 event observed, we have the problems, the current models, they cannot account these neutrinos, and we should explain more, we should use more advanced like 2-zone or other scenarios to be able to account for these events. But what is important that now we are in the state that we have a lot of data and many different phenomena we could see by multi-messenger point of view using 2 different windows. And this is actually great because we can investigate the processes in much deeper and understand blazars and the processes responsible for the emission. So this is the end of my presentation. Thank you for your attention.
Thanks a lot. Thanks a lot, Narek. Wonderful talk. We have time for 1 question, perhaps. Anyone?
May I ask a question?
Yes, please.
Yes.
Introduce yourself, please.
Hi, Narek. Very nice talk. So I think based on your simulation and your model here, actually, I think it already implies this. There are multiple radiation zones in blazar jet. For example, in this in your 2021 MNRIS paper, you fit this the spectrum at different time, but it seems that it's changed very quickly. The spectrum and also the parameters are not very are not all identical. I mean, for at a different time. So this I'm not sure if there is only exist one zone, whether the parameter could change so rapidly. But it seems to me we need a multiple zone. I mean, even more than 2 zones to explain the phenomena. Do you have any?
Yes, you are asking about neutrino or for the other blazars? You are asking about the neutrinos, yes?
I mean, in general. I mean, I would say the one zone model is actually probably is not a physical model. I mean,
well, yes. I agree with you. The point is, like, up to now, we have so much data that is coming every day. So people are not trying to develop more complex scenarios to see how you have this many interaction zones or etc. But I believe I agree with you that in the end there should be much more deep simulations to show that there is no single zone that is contributing, and there are much more complex. I mean, it's not whatever we do now or however we interpret this emission from blazars. I think it's a simplified view, because what we say that is one region, that this region is dominating. But I think I agree with you that more complex emission zones or emission scenarios are needed to explain this, especially after these neutrino observations, that we understood that there are more problems than we knew before. Yes.
Okay. Yeah. Thank you.
Thank you very much. Thanks for the questions and the answer. We appreciate that. Sorry, we are limited by time now. And I would like now to ask Professor Lorenzo Amati, who's going to be talking about how to do cosmology with gamma ray bursts.
Yes. Hello, good afternoon. Can you hear me?
Yes.
Hello, this is Lorenzo Amati. So I'm going to share my screen now. Let me. Okay, you should see it. So can you see my screen?
It's coming up. Oh, yes, we have it. Yes. Thank you.
Thank you very much to you and all the organizers for inviting me to give this talk on gamma ray burst cosmology at this very interesting and valuable conference. So this is Lorenzo Amati from the Italian National Institute of Astrophysics. And gamma ray burst, and especially gamma ray burst cosmology, are my main field of research, including the study of next generation gamma ray burst instruments and space missions. So as we know, we already heard very nice summaries about gamma ray burst basic properties also this morning, thanks to Massimo Della Valle and Luca Izzo, for instance. So we know that gamma ray bursts are the most extreme electromagnetic phenomena in the universe. We know that they come mostly in two main flavors, short ones and long ones, where more or less short ones last less than a couple of seconds, whereas long gamma ray bursts last typically tens of seconds or even several minutes. And most important, there is mounting evidence of different origin of these two main classes of gamma ray burst. And then, of course, there are also many investigations aiming at distinguishing between different subclasses within these two main classes. So long gamma ray bursts basically are coming mostly from the core collapse of peculiarly massive stars, whereas short gamma ray bursts are mostly due to neutron-star black hole mergers. There are several evidence supporting this scenario, but this is not the main subject of this talk. The main subject of this talk is to show the great potentialities of long gamma ray bursts for cosmology. This is due because they can be detected up to ratio 9 of 10 thanks to their huge luminosity index and gamma rays. So just to give you an idea, they can release more than 10 to 50 to the 4 ergs in a few tenths of seconds in the X gamma rays. They are followed by the so-called afterglow emission, which is a multi-wavelength exponentially power law fading emission. And of course, this makes them very interesting because they can be detected up to the very early universe. The investigations aimed at full exploiting gamma ray bursts for cosmology belong to two main lines of research. First line, as I summarized here, is to use them for investigating the early universe, which means cosmic organization for stars, for galaxies, as I will show in a while. The other very interesting line of investigation is instead of trying to standardize them, so to use this phenomena to investigate cosmological parameters and ultimately, for instance, the nature of dark energy. So concerning the early universe, we know that main issues in modern cosmology deal with the first epoch of the universe, which we mean the first billion years of the universe. So after the recombination, when the CMB was released, and the universe was mostly opaque, composed by neutral hydrogen. This is true until a few 10 million years after the Big Bang. Then first stars, first galaxies start to form. They start to illuminate the intergalactic medium. And the first generation of stars are supposed to be the main source of the ultraviolet photons that are needed to explain the cosmic ionization, which is a process occurring between more or less redshift of 8, 8.8, up to a redshift of more or less 6.5. And as we know, nowadays, the hydrogen in the universe is mostly fully ionized. So what were the main sources of cosmic ionization? What are the characteristics of the first population of stars and galaxies? How was the metallicity evolution in the first 100 years, million years after Big Bang are main open questions in modern cosmology. And gamma ray bursts, as is shown in this sketch, where they are put in the cosmological context, as you can see, their redshift distribution and their detectability up to a redshift of 9 or 10, which means a few 100 million years after the Big Bang, bridge us from the local universe up to the so-called cosmic dawn. So this epoch during which first stars, first galaxies were forming, neutral hydrogen was getting ionized. Their power comes also from their association with massive exploding stars, which die where they were born. So an exploding gamma ray burst is also tracing a star-forming region within a star-forming galaxy. So to give you an idea of the power of gamma ray burst for these studies on the universe, if you see on the bottom left, this is the picture, so a direct image of the near-infrared afterglow emission following the explosion of the farthest away gamma ray burst ever detected. This is at a ratio of 9.2, 9.4, which means 400 or 500 million years after the Big Bang. So it is true that at this very early epoch, there are some detections of very recent detections, for instance, thanks to the Hubble Space Telescope, the field, frontier field, of very bright primordial galaxy, mostly detected through lensing, but this is instead a direct detection of an exploding object at this very high ratio. And this is possible only thanks to gamma ray burst. So for instance, if we could get a statistical sample, so several tens of gamma ray burst at redshift higher than 6, up to a redshift of 9 or 10, we could reconstruct, given that these long gamma ray bursts are associated to the star formation rate, and there is evidence that at redshift higher than 2 or 3, when there was the peak of star formation rate in the universe, there are good tracers of star formation rate evolution. We can solve the large uncertainties on star formation rate evolution from redshift 6 up to redshift of 10, as is seen on the picture on the right, where you can see this stripe, the gray and dashed line regions, show you the large uncertainties that are coming from current measurements and extrapolation from the very few galaxies that have been detected at redshift higher than 6. And in green, you see the points showing the star formation rate evolution that you can infer with the current sample of gamma ray burst, which is a very limited sample at redshift higher than 6. And as you can see, there is a large uncertainty. Instead, in red, the red dots are the points showing the kind of accuracy you could get with a statistical sample of gamma ray burst at redshift higher than 6. To give you a more even a more relevant flavor of the power of gamma ray burst, here there are 6 images taken by the Hubble Space Telescope in the direction of the 6 highest redshift gamma ray bursts ever detected, that are higher than 6, 7, or even 8 or 9, so hundreds of million years after the Big Bang, and you can see there is nothing. So after the fading afterglow that you can see on the top left, this is a typical picture. So when if you follow up the gamma ray burst that is detected in the X gamma rays with a telescope, a large telescope, you see this fading light. But when this light is faded away, there is nothing. So you know that in these directions, at this redshift, there is a high redshift galaxy only because we were capable to detect the gamma ray burst and localize it in the X gamma rays, to follow up it in a very efficient way with ground telescopes and do absorption spectroscopy and localization of the fading afterglow. So we know that these galaxies exist, where they are, how many they are, and they are below the detection threshold of the Hubble Space Telescope. And this will also be true in the next years, of course, with a very lower threshold, so to higher sensitivities, with JWST or ELT or the extremely large telescopes of the future. The power of gamma ray burst, of unveiling, so detecting, localizing, measuring the redshift of the bulk of the population of primordial galaxies that are below the detection threshold of even the largest facilities in the optical and near infrared. But not only of these gamma ray bursts that are invisible, of these galaxies, host galaxies that are invisible to the largest telescope, we can know that they exist, how many they are, and so on. But thanks to the absorption spectroscopy of the fading afterglow, again, these fading lights that you can see on the top of the light, if we are very quick in following and catching this fading light, we do absorption spectroscopy, and of this invisible galaxy, we can infer the metallicity, as you can see in this example of this spectrum on the bottom, the metallicity, the neutral hydrogen fraction through the study of the Lyman alpha neutral hydrogen line, and also the characteristics and the degree of ionization of the intergalactic medium. So clearly, this is our information of paramount importance for assessing the properties of primordial galaxies, for assessing the metallicity evolution of the early universe, for assessing the evolution of cosmic ionization. And of course, we also expect that gamma ray bursts may pinpoint the very first population of stars, the so-called POP3 stars, that are whose detection is still beyond the limits of any optical or radio facility. So these properties, this power of long gamma ray bursts for investigating the early universe, are very well known to cosmologists. But here, the main issue is that, as can be seen here in this distribution of gamma ray bursts as a function of redshift, we have only a few gamma ray bursts detected and identified at a redshift higher than 6. This is because despite the efforts in the last almost 25 years, since we were able to measure the first redshift of gamma ray burst at the end of the 90s, despite huge efforts from space facilities, ground telescopes, the inefficiencies in this observational process is leading us to having only a few gamma ray bursts at redshift higher than 6. So the main objective of next generation gamma ray burst missions for the end of this decade or the next decade for the 30s, and here I mention some of them, is to fully exploit gamma ray burst for cosmology and for investigating the early universe in particular, and also, of course, for other application of gamma ray burst that, as you know, are phenomena which have interest for many fields of modern astrophysics. But focusing on cosmology, we have this mission concepts, TSEUS Europe, Gamma in Japan, TAP, which is Transient Blasters probe in the USA, also Gamma Explorer, different sizes, but similar concept. So to show you a showcase of how this next generation mission will allow us to actually overcome the current limitation and get several tens of gamma ray bursts, so primordial galaxies, at very redshift in very few years of operation. Of course, I show you the TSEUS Transient Energy Scan Lunar Surveyor example. TSEUS is a mission project which is carried on by a large European collaboration, a consortium which is led by Italy, UK, France, Germany, and Switzerland, with myself as a coordinator, and was selected by ESA in 2018 for a Phase A study, a 3-year Phase A study, which was ended in June. And despite ESA at the end selected for a medium M5 mission for the 30s, a mission to Venus, so a completely different field of science, because of their vision, their strategy, this project of course continues and takes advantage of these 3 years of development. the concept of TCUS is the same concept as all the other missions that I mentioned, the future next generation mission. So the idea is to overcome the current limitation of GRB detectors, which is the energy band. So if we want to increase substantially our capability of detecting high redshift, very redshift gamma ray burst, we need to extend the monitoring of the sky over a broad field of view. We are hunting very redshift gamma ray burst. We have to extend to the soft X-rays. So the idea is to couple, from the case of TCUS, two kinds of gamma ray burst monitors, one extending down to 0.3 keV with an unprecedented sensitivity, and one extending up to 10 eV, so to be able to detect and localize any class of gamma ray burst, and in this case especially high redshift gamma ray burst. And then the spacecraft, the satellite, should be able to slew, so to point in the direction of the gamma ray burst detected by the monitors within 1 or couple of minutes, like the SWIFT mission is doing in the X-ray, but in this case we need follow up in the near infrared to be able of catching and localizing and measuring the redshift of the near infrared fading after that I showed you at the beginning. This fading light that is key for localizing and identifying and measuring the redshift of this very primordial gamma ray burst hosted by very primordial invisible galaxies. So this is to show how such a mission in only 3 years of operation, so if we think that now these missions can operate more than 10 years, but this is only in 3 years of nominal operation. This is the current situation with the distribution of gamma ray burst as a function of redshift. You can see on the right, gamma ray burst, current distribution of gamma ray burst as a function of redshift in a cosmic cone, so in a cosmic context. Still, you can see a very few of them at redshift above 6. Instead, with a machine like TCUS, okay, now there is a glitch in the slide, but this region will be completely filled by TCUS gamma ray burst. Sorry. Okay. As you can see, there was sorry for this glitch in the presentation. So these red points, so you here, this is the current situation, and here the red dots are the gamma ray bursts that will be detected and localized by a machine like TCUS. So producing really a substantial advance in the detection, localization, identification of redshift gamma ray burst, and really enabling gamma ray burst cosmology. These measurements by a mission like TCUS will be also joined to the follow-up efforts by next generation ground telescopes like the LT or TMT, so these 30-meter class telescopes in the that are being developed that will be capable of following up the gamma ray burst detected by a machine like TCUS and doing high-resolution spectroscopy, for instance. And all these efforts will produce this kind of improvements that I already showed before in the determination of the star formation rate evolution. So you see here, the red dots are those expected from gamma ray burst from a machine like TCUS, a substantial improvement with respect to current situation. Or, as I mentioned before, a key measurement or key capability of this mission is to detect and localize invisible galaxies that are below the detection threshold of near infrared and optical telescope. And this has an important, very important impact on the investigation of the cutoff in the luminosity distribution, so the faint end of the luminosity distribution of the galaxy. As you can see in this sketch, there is a large indetermination in how, at what magnitude is this cutoff. And this produces a large indetermination in the quantification of the bulk of the population of primordial galaxies, and also the star forming rate in this invisible galaxy. And this also, of course, is linked to the issue of determining the star formation rate evolution. So with a machine like TCUS, with 40, let's say, gamma ray burst than 6 in 3 years, this is the accuracy in the red curve with which one could determine the cutoff magnitude in the primordial galaxy luminosity function. And the same, this is showing the capability for cosmic ionization. So as I mentioned at the beginning, cosmic ionization is supposed to be sustained by the first generation of stars. So ultraviolet photons produced by the first generation of stars have to escape the primordial galaxies and the host galaxy and reionize the cosmic medium. So to do this, you need to have a combination of escape fraction of which is Fs here, escape fraction of luminosity of ultraviolet photons from the host galaxy, and compare to the production of ultraviolet photons. So this is putting together the star formation rate evolution with the properties, so the neutral hydrogen fraction and the absorption capability of this primordial galaxy. And here the red line shows the limit. So if we stay above the limit in this plane, the star really ionization can be explained by force population of stars. If we stay below, this will be really an issue, and alternative mechanism should be invoked. And as you can see from these contours, both the blue and the cyan ones indicate two different cases for which a machine like this use could produce constraints on cosmic ionization. And the same, again, this is showing the metallicity evolution, so the cosmic chemical evolution at very high redshift, as could be determined by a machine like this used for gamma-ray bursts, which are the green and the red dots, extending current measurements that are the gray and blue dots here. So this is clearly a breakthrough at which gamma-ray burst experts and next generation mission are aiming at. So providing a substantial contribution in synergy with next generation facilities, or also SK in the radio, for instance, for the early universe. But the other phase of gamma-ray burst cosmology is to use them for investigate cosmological parameters and ultimately testing cosmological models and, for instance, properties and evolution of dark energy. So why we would like to exploit gamma-ray burst for this task? Again, here the key properties are the ratio distribution, the capability of detecting gamma-ray burst up to a ratio of 9 or 10. If we think that type 1a supernovae are limited to 1.4, 1.7, 2 in perspective, that baryonic oscillations are limited to 2 or 3. So clearly having a standard cosmological probe or a standardizable cosmological probe extending the Hubble diagram up to redshift of 9, like gamma-ray burst in principle could do, would be really a breakthrough. As you can see here in this classical plot on the left, this is an omega m, omega lambda plot. So, you know, of course, the critical density of matter versus the cosmological constant or dark energy density. You see that different probes here, the CMB, the clusters of galaxies, supernovae, produce different orientation because they have different ratio distribution and they use different methods. Also, as the famous case of type 1a supernovae is teaching us, each of these probes is characterized by systematics that are not still fully understood. Here there is a quick list of possible systematics affecting type 1a supernovae. There have been also recent works questioning the actual reliability of type 1a supernovae as cosmological probes, but this is just an example. So adding more cosmological probes produces different sensitivities and more and less reducing the systematics on the measurement of cosmological parameters. And what we are aiming at now, we know, as is sketched at the top of this figure, that the combination of the measurement of the CMB, type 1a supernovae, the prediction of inflation, large scale structure, baryonic oscillation, and so on, are giving us this picture in which the universe is mostly flat, and there is this 70, more or less 70%, of, which is due to the cosmological constant, to dark energy, to something different. And this is what really we want to go also with new probes like gamma-ray burst. So from one side, for instance, investigating models and evolution of dark energy, on the other side also testing different cosmological models or variations of the standard general relativity to explain these properties of the universe. So how can we actually standardize gamma-ray burst? Gamma-ray burst index gamma rays are not standard candles by themselves. Their isotropic released energy spans several orders of magnitude. It can go typically from 10 to 49, 10 to 50, up to more than 10 to 54. However, there is a key observable in gamma-ray burst, as there is in type 1a supernovae when we consider the Phillips relation that is used to standardize type 1a supernovae, a relation between the peak magnitude of the supernova light curve and the stretching of the light curve. Here, the key parameter is the spectral peak energy. As you can see on the bottom left, the gamma-ray burst spectrum shows is characterized by a smoothly broken power law continuum. And if you look at the bottom panel in the left figure, if you quantify it in terms of nu f nu, it shows a peak. The photon energy at which the spectrum peaks is called the spectral peak energy. And as you can see in the figure on the right, there is a strong correlation between the spectral peak energy and the total released energy of the gamma ray burst. So here we have a correlation between an observable, cosmologically independent observable, the spectral peak energy, and a quantity, the isotopic released energy, that of course depends on cosmology. This is also sketched here. So in principle, we have in our hands a tool to standardize gamma ray burst in a way similar to what is done with type 1a supernovae, using the peak magnitude again and the stretch of the Lie curve. Here, the problem is that we don't have a statistical sample of low redshift gamma ray burst. So differently from type 1a supernovae, we don't have a sample of gamma ray burst at very low redshift. Most of gamma ray burst at redshift are then 0.1, 0.01, but all at redshift for which the cosmological effects are already there. So we discovered this correlation between these two quantities because we assumed a cosmological model to compute the isotopic released energy through the luminosity distance, which of course depends on the redshift, on the Hubble constant, and other parameters. But we can, in any way, implement methods to avoid this kind of circularity, so we can fit, as is done partly also for type 1a supernovae or other cosmological candles, we can fit all together the cosmological parameters and the parameters of the correlation. So the first, let's say, call it exercise, but the first demonstration, if we could really use this correlation for extracting information on cosmological parameters from gamma ray burst, we did it in 2008 with the peak ISO correlation with Massimo Della Valle and other colleagues. We asked ourselves what happens to the scatter of the correlation, the dispersion, and the goodness of fit of the correlation if we assume a flat lambda CDM model, flat universe with only omega m free to vary. And what we obtain is what we see in this figure on the left, where we actually discovered, we found that actually the goodness of fit and the scatter, the dispersion of the correlation, is a function of the value of omega m that is assumed to compute the value of the isotropic energies. So here we actually are marginalizing, let's say, over omega m in our fit. We see that the chi-square, but also the likelihood as a function of omega m as a nice parabolic square shape, minimizing at omega m around 0.3. So, which means that if we didn't know anything about type 1a supernovae, we didn't have any other cosmological probe, with the simple assumption that we live in a flat universe as the inflation is predicting, of course, and the CMB is telling us. So without any other probes in addition to this, based only on gamma ray burst, thanks to this correlation, we could say that omega m is 0.3, so that the universe is actually accelerating, that omega m is lower than omega tot, and there is this additional, let's say, cosmological constant or dark energy or whatever. If we release the flat lambda CDM hypothesis, we can also draw a contour, as you can see in the right, in the omega m, omega lambda plane. And this is a quite old, 10 years old plot, or even more, but shows you that already more than 10 years ago, gamma ray bursts through this method were competitive, the contours from gamma ray bursts, with those that could be derived through type 1a supernovae or other methods. And this table shows the perspective in the evolution of the accuracy in the measurement of omega m through gamma ray burst with the increasing of the sample. Nowadays, we are around 200, 250 gamma ray burst with measured redshift, with measured spectral parameters that we can use for standardizing them and doing cosmology. And here you can see also simulations on the accuracy that we could obtain for even larger samples. And also in the second part of the table, the bottom part, shows you the kind of accuracy that could be obtained if we manage to calibrate the correlation. As I mentioned at the beginning, there is this circularity problem. We cannot calibrate the correlation with very low redshift gamma ray burst, but there are, we can calibrate them against type 1a supernovae, for instance, the low redshift ones at least, or through other methods, in which case the accuracy would improve significantly. On the right, we show the possibility of investigating the properties of and the evolution of dark energy by using, for instance, the standard CPL, so Chevalier-Polarsky-Linder parameterization of dark energy, you can see the red contour is what could be obtained with a very large sample of gamma ray burst compared to what can be obtained with type 1a supernovae, barometric cushion oscillation, and CMB. This is thanks to the fact that gamma ray bursts extend the Hubble diagram to very high redshift. So despite the transition between the dark energy dominated universe and non-dark energy dominated universe is around 0.5, something like this. To determine this evolution, you need to measure the Hubble diagram up to very high redshift. So other approaches, of course, the peak isocorrelation that I discussed up to now is the most investigated tool. But there are the ones, for instance, you can use the peak luminosity of the burst instead of radiant energy. You obtain similar correlation results. You can, as I mentioned, calibrate the correlation against type 1a supernovae, which provides you additional accuracy, but of course in this case you are no more independent cosmological probe. You are calibrated against another probe, and so you carry on with you bring with you all the systematics of the other probe, so you extend the capability of the other probe. Techniques for self-calibrating the correlation are also under study, and of course other interesting correlations involve the use also of the afterglow properties, not only the prompt X-gamma ray emission like the peak ISO, but also the luminosity of the X-ray afterglow, the duration of the plateau in the X-ray afterglow, and so on. So I now come to my conclusion. I just would like to mention that very interesting use of gamma ray burst is also the testing, use them for testing fundamental physics. For instance, as you may know, quantum gravity scenarios predict that there is a Lorentz invariance. So if you take a source like gamma ray burst, which slide a very, very high redshift, which emits over a very broad energy band, you expect a delay between low energy and high energy photons, and this delay is linked to the quantum gravity mass. And this exercise in perspective is very useful. This has been done on some gamma ray burst, but it's very useful in perspective. So I conclude here. With this summary. So as I try to show very short in this talk, to give you a flavor of the high potentiality of gamma ray burst for cosmology, early universe, cosmological parameters. So first stars, first galaxy, community ionization on one side, cosmological parameters, dark energy, and so on the other side. Next generation GRB mission, like the TGUS that has been studied by EASE and is being carried on for the next year by a large European collaboration, or other missions in the USA or in Japan or worldwide, are aiming at fully exploiting gamma ray burst in this direction. And so, of course, if you're interested in this kind of mission, especially in TGUS, I refer here to the website and to all the papers that have been published on this mission concept and on this science case on the web. So thank you very much.
Thanks a lot, Professor Mercy. We don't have much time left. If there is a quick question, we will be happy to have right now. Any questions from audience? If not, well,
I have
thank
one.
you very much.
I have one. Can I?
Yes, please go on. Please go on.
Okay, Lorenzo, thank you for the nice talk. Actually, my question is related to last point that you mentioned about this different velocity of different frequency of the gamma ray burst. So in this case, you have to assume both the high energy and low energy emission comes from the same place or the same location. Am I right in this case?
You are perfectly right. This is the main drawback of this potentiality of gamma ray burst. This is the problem. Yeah, this is the question. The question is that in principle, gamma ray bursts have the right properties for testing Lorentz invariance to very, very good accuracy. But unfortunately, you cannot still account properly, or you have to make assumptions on the prompt emission mechanism. So it is true that it is believed that prompt emission, so emit as a prompt emission, the prompt burst is thought to be emitted from a same region from a main emission mechanism, so which goes, which could emit photons down to the X-rays and up to the GV. As this is one case, you show on the right the light curves of a gamma ray burst detected by the Fermi GBM from, you see light curve from 8 keV, so the top panel, the green light curve, up to the GV. But of course, there is observed intrinsic delay between the peak of the light curve at different energy. And the issue is to disentangle the effect due to quantum gravity to the intrinsic effect due to the physics of the emission of gamma ray burst.
Well, thank you very much. Thanks for the questions and also the response. So we would like to conclude this session and hand it over to Dr. Shakari for continued discussion.
Okay, thank you so much, Habib. We have actually a break now around, let's say, 12, 13 minutes. So we will come back at 5:20 in Iranian time and 2:50 in CET time. So just I will write here to remember. So see you in 10, 12 minutes.